But this is a great time to be in computer science. And obviously the reason is because computing is being reinvented for the first time, as dramatic as it is, for the first time really in about 60 plus years. The computer that we know of, that you all use, and our computing model, our mental model of a computer, the architecture of a computer, how you write the program, run the program, how you think about even taking computers to market, what it's used for 64 years, it has been largely the same since the IBM System 360. In fact, my first architecture book for learning about computer architecture was the System 360's manual. And so a lot has changed as we went from PCs to internet and mobile and cloud and all those things. But the fact of the matter is the computing model, the fundamental part of computer science, has largely remained the same until now. For the first time, the way you write the software, how you process the neural network versus the software, and what the applications can do has now dramatically changed. Everything is fundamentally different. At the highest level, one simple way to think about it is computing as we knew it before was largely pre-recorded. It's content that we pre-recorded, images, videos, software that we largely pre-recorded. But now everything is generated. And the nice thing about generating everything in real time is that it could be contextually consistent, contextually relevant to what it is that you're dealing with. And of course, it can respond to your intention, not just explicitly to the things that you instruct. And so the computer is fundamentally different in that way. Now the question is, what does that mean at every single layer of the stack, from how the software is now developed, the methodology of it, how you organize your company to be able to develop software of today, completely changed. And so the methodology, the tools we use, the approach that we think about software coding, completely changed. How we run the software, neural network versus compiled binaries, very, very different. And so what does that mean to the computer system, the network, the storage? What does that mean to the software stack and the cloud services that sit on top of that? And of course, everything about the applications. What did it open up? And somebody just came and said, this piece of software we just opened up called Alpamayo. And I've been working on self-driving cars now for about 13 years. And the days of robo-taxis are going to be literally everywhere. Everything that moves will be robotic. And that's an example of an application that we wouldn't consider doing until deep learning and artificial intelligence came along. That was such a big unlock that, I said, hey, aha, all of these problems that we wanted to solve in the past that we needed computer vision for, really are now fundamentally unlocked. And so it's how you think about every single stage of that. What is a software engineer? How do you organize the company? What is a computer for the age of AI? How do you architect that? All the way to what you can use it for, and therefore where you would deploy it. All of that has fundamentally changed. And for me, the journey really started about 15 years ago. And I had the benefit of seeing some early works in the area. And as all Stanford students do, you break the problem down, you reason about it from first principles, and you come to the conclusion, literally everything has changed. And so here you are, computer scientist students. This is really the first generation of AI becoming useful. And where we, a couple of years ago, was in the generative part of AI. And as you guys know, generative AI not only made it cool for us to do image generation and text summarization and translation and whatnot, but generative AI also enabled us to think. And so when I saw generative AI, what other people saw was that it was able to generate images, and I surely would appreciated that as well. But the fact that you can generate thoughts in the form of images, but you can generate thoughts, you can also reason with it. And the ability for AI to think after GPT was very, very obvious. Now the question is how would you train, how would you fine tune an AI to be able to reason step by step by step, and how would you teach it how to do so at fairly large scale in a kind of semi-supervised way? And so those are kind of the engineering problems you had to solve. But the moment you see GPT, you say, aha, thinking is just around the corner. And thinking is generating tokens that you consume internally, and generating tokens that you consume externally would be called tool use. And so the idea that after GPT happened 2 years ago, that we would be at this moment was fairly easy to predict. Now, of course, unbelievable amount of technology was invented, and a lot of amazing people did amazing work, but you could almost see that moment here. And so here we are. You now have agentic systems. And so now the question is what's next? And what happens in a world where a computer is not responsive to what you ask it to do? It's not on demand. Today's computing is really on-demand computing. The word on demand was actually created in our generation to talk about how you think about using computers. Time-sharing computers that you would use on demand became cloud computers. And cloud computing, of course, is on demand, but in your new world of agentic system, the computers are now continuously running. And so what happens in a world where the computers are continuously running? What happens to cloud services? What happened to your personal computer? What happens to, all of these different systems? Now there's a great opportunity again to rethink all of that. And so what I, is kind of like my introduction to everything about computer science has changed, and everything about every field of science has changed because of the things that we've changed. And so this is a good time to go to school.
Okay.
Co-design is super interesting. And basically co-design said back in the old days, we abstracted computing so that the people who design microprocessors, people who worked on compilers, and people who worked on languages, and so on and so forth. You guys know that. And we actually had different fields. But the problem, and in fact, this happened at Stanford. What's the beauty of RISC? What was the beauty of the work that John Hennessy did? The beauty of it is that you got to think about compilers and microprocessor architectures harmoniously, co-designed, because otherwise you could end up creating a microprocessor that's super, super tight, and everything is maximally optimized. But unfortunately, it's hard to compile. It's difficult. It's not compilable. And so they created a simpler instruction set that exposed simplicity to compilers so that compilers could do a better job generating code. And it turns out a simpler machine co-designed with a compiler creates better performance than two systems that were optimized individually. That's very Stanford. Okay, this is part of your heritage as all of your in John Hennessy's trail of amazing work that's left behind. And so you take that and you think about, well, what happens in the post world of general purpose computing? Why is it that every problem in computer science would be solvable by a general purpose instrument? At some level, you could say, well, if you had a general purpose instrument, you prefer that. However, there are some extreme problems, whether it's computer graphics back in the old days, or molecular dynamics, or quantum chemistry, or fluid dynamics and large multi-scale, mesoscale multi-physics problems, or deep learning. These problems are so computationally intense. Why would you use a general purpose computer to go do that? And so the big insight is, what if you understood the algorithms, understood the computer systems, understood the if you will, the compilers, the frameworks, and understood the architecture of chips, and you were optimizing all of it at the same time. And so the facts, here are the facts. This is what happens when you do it, what I just described. NVIDIA is probably the first computer systems company that's extreme co-design, meaning we literally co-design across all of that, and including CPUs, GPUs, networking, and switches, and everything, and storage. And so the question is, what do you get? Well, Moore's law back in the old days, you guys all know about that. Moore's law was about 2x every 18 months, so call it 10x every 5 years. Okay, so 10x every 5 years is 100x every 10 years. And that was in the good old days of Moore's law. And for all the computer scientists in the room, you know that Moore's law was underpinned by a concept called Dennard scaling, and Dennard scaling ran out of steam several years ago, probably about a decade ago, in fact. And we kept squeezing it, but over the course of last 10 years, if you just allowed microprocessors to continue to scale and you just don't touch the software and you just benefit from the speed up of semiconductors and microprocessor design, you, at best case, you would have gotten 100x, but probably because Dennard scaling slowed down and Moore's law largely ended, you probably got something along the lines of 10x over the course of 10 years. Well, in the case of NVIDIA and co-design, we got 1 million x over 10 years. 1 million x. And so somewhere between 100,000x and 1 million x. Okay, so there, when you're talking about numbers that big, it really doesn't matter. And so 1 million x over 10 years, we were able to get scaling and computation scale so large, so fast that AI researchers say, why don't we just take all of the internet? Why even worry about what data to go curate and what data to create? Let's just take all of the world's data and just give it to the computer. And that's really the big breakthrough. When you're able to do something so insanely fast, for example, if you were able to travel at the speed of light, where we choose to live doesn't matter. If you were able to go from New York to California in 10 minutes, our freedom, everything about society would change, right? And so if you're able to do computing 1 million times faster, everything about computing changed. And that's really the big breakthrough. Because of co-design, because of the way NVIDIA approached it, we accelerated computing by so far that it created all this infinite abundance opportunity for everybody to think about the future. And so anyways, here we are.
Cool. How should education evolve in response to the industry as it's changing?
Yeah, and that's a really excellent question. And I think the answer clearly is AI should be part of your curriculum, not just in learning about AI, but using AI for the curriculum. The problem with textbooks, as you know, it takes an enormous amount of effort to do. And when I was taking classes at Stanford, Professor Hennessy was still writing his textbook. It was all handwritten out. And each week, it seemed like he was writing a chapter. I don't even know how he writes a chapter a week, but every week he was writing about a chapter. And then over time, all of those notes turned into a textbook, into the first edition. And that must have taken several years. And so I think it's not possible for universities, for pre-recorded textbooks to keep up with information and knowledge that's being generated in real time by AI. And so I think the future probably has to be some union of the two. And I don't know about you guys, but I can't learn anymore without AI. And so not only do I have the AI read the papers, but I also have, once it reads the papers, I might ask it to go read a whole bunch of the other papers that are associated with it. And then now it becomes a super researcher. And then I can first I ask it to summarize, I ask it some basic questions. And then after that, you interact with that paper as if it's a researcher that's dedicated to you. And so most people don't realize that. I think a lot of people still think that you summarize a document, but in the process of summarizing the document, that AI learned a lot. And so, I think that in the future, I do hope that curriculums are tightly integrated. I will say, in defense of the textbooks, though, I will say that first principles don't change. In the final analysis, Mead and Conway is still a solid of fundamental methodology as before. It is true that the scaling process that led to constant current density, constant power density, all of those design optimizations associated with modern semiconductor design, we've kind of exhausted all of that. None of that is ISO anything anymore. And so, but it's still good to know where we came from, and so I would still encourage that to appreciate the first principles. And while I was going to Stanford, I was already working at AMD and I was designing microprocessors at the time. And it was still really good to see simultaneously how we design things in practice versus the first principle methods associated with learning about eventually how to design these things. And And I really enjoyed having, feet on both sides of it. And I ended up learning a lot more. And so what that means is when you're using AI, which is real world, it's contextually relevant now. It's contemporary. And meanwhile, you have first principle knowledge that you're learning at the same time. You're kind of getting the same thing that I experienced.
The question is,
first of all, NVIDIA uses more Anthropic and OpenAI tokens than just about anybody. And the reason for that is obviously we do a lot of coding, we do a lot of design, and 100% of our engineers are now agentically supported. And so I want them to be working with agents using the latest generation tools and modernize how NVIDIA does work altogether. Okay. So number one, if you can use OpenAI and Anthropic, I would highly recommend you use it. And the reason for that is because it's useful. It works really well. It's getting better all the time. And it's, as you know, large language models is the technology inside, but Claude is a product, and Claude Code is a whole harness around it. And that harness is getting better all the time. The model's getting better all the time. It's not likely that anybody open source, go to GitHub, download something, it's going to work nearly as well. Okay, so I highly recommend, and we do, use off-the-shelf frontier AI models. The question is, why is it there that we're advancing and working so hard on open models? The reason for that is because language models are very important because they represent the codification of our intelligence, and we want to automate ourselves, especially is a very important part. But you need to know that AI is about learning the representation, the meaning, the structure of information. And so the question is, where is information? Well, we're living in information right now as we speak. The reason why there's structure is the reason why every day you show up, it's kind of largely the same. Otherwise, it'd be like practically white noise. And so the fact that biological systems and physical systems have structure, and from that structure, I must be able to learn higher level representation. And if I can learn the representation, then I could manipulate it. Does that make sense? And so just because I can learn the representation of language, I can then generate it, I can manipulate it, I could put it to use. And so I want to do the same thing for chemicals and proteins and genes and physics and physical systems, robotics, for example. And so notice the way you represent all of those things are fundamentally different because the structure is different and the dimensionality is different. How you train it is fundamentally different. Right.
The question is how best to spend their mental faculties over the next few years.
Yeah. So first of all, on the pain and suffering comment, there's some advice that says you should choose what you love and what you're passionate about. That's what your career should be, and I think that's terrific. I think that's terrific. If you happen to know what you're passionate about, if you happen to know what you love, but I think there are a lot of people who don't know what they're passionate about and they don't know what they love. And the reason for that is because nobody knows everything. How could you know what you don't know? So in a lot of ways, the idea that you would only choose careers that give you passion, that gives you, makes you happy, is a bar that I think is too high, number one. And the reason for that is because whatever you decide to do for a living, whether it's you found something that you're passionate about, or this is your job. And in my case, it used to be cleaning toilets and bussing tables. It was my job. And I will do the best I can in my job. Whatever you give me as a job, I will do the best I can possibly do. And I do that today. Now, there's a misunderstanding that somehow CEOs, we love our job, and many CEOs, I'm passionate about my job, I love my job. They're lying. There's not one CEO who can say that from the moment I wake up to the moment I go to bed is just zippity doo dah. The fact of the matter is, I really love doing 10% of my work, and 90% of my work is hard. And I do it to the best of my ability anyhow. And I suffer through it. I literally suffer through it. I prefer to do something else, that other 10%. But that other 10%, there's only so much quantity of that. And every company has abundance of problems, and there comes in different types. And you're going through life, you're going to have abundance of problems that are going to come in different types. And you just have to learn how to condition yourself to want to get to a better state, no matter how hard, to get better, no matter how hard. And that's suffering. You know, you don't like doing it, but you're doing it with all your might anyways. What do you call that? That's suffering. And so I think that when you suffer and you have the benefit of struggle, and you're being presented with many opportunities like that, it teaches you resilience. And when the time comes and the world or your family or your company or your colleagues, they need you to be tough. They need you to be resilient. They just need you to be able to fight through it. You can't have you don't have that character about you. You don't have that muscle unless you've gone through it a whole bunch of times. And so, you know, I'm advising that you not seek for just joy, that you also seek for some pain, some suffering, because you're going to need it someday. And then lastly, it's just your job, you know?
As Preacher Huang once said, don't wake up with a loser mindset. The question is, what's your favorite order at Denny's? What is the best and worst part of your job?
When you're CEO of a company, you have the benefit of a lot of really fun things. Like, for example, you're really the person who has to conceive of the intersection between vision and strategy and execution. Okay. And so you have to live in that world, and it gives you, and when you're a company with capability, and I'm surrounded by amazing computer scientists, and many of them from Stanford. And when you're surrounded by people like that, when you have a vision, it's very realizable. And because you're with amazing people, your vision is more ambitious. Okay. And so I think that's the fun part. The not fun part. So that fun part, I get to do almost all the time. I'm always constantly updating my view of the future and my vision of the future, and our role in it, and how we ought to reinvent ourselves so that we could, you know, contribute more to that future, or go invent that future in the first place. And so as a CEO, you get to live in that world, and that's fun. It's very imaginative. It's very strategic. It's, you know, highly complicated. There's no right answer. And in a lot of ways, it's creativity at its most. Okay. On the other hand, what comes with that power is the responsibilities for a bunch of people who joined you in that spaceship, that joined you in that vessel, and they want to help you create this future, and they're part of your team, and you feel a deep responsibility for their well-being. And so when the company's not doing well, or the company in the older days, you know, when we were in the beginning trying to find our way, we probably nearly went out of business, you know, 4 or 5 times. I mean, literally almost went out of business. And we were on fumes, or we're really flat on our back. And so during those times, it's embarrassing, it's humiliating, it's hard. You don't know what the answer is. Oftentimes you're in the dark, you're afraid, you know, all of the feelings that we have as humans, just multiplied by, you know, 1,000, 1,000,000. And you know, when you're a public CEO, your face is always out there. And when you do well, people are happy. When you don't do well, they're fast to tell you. And so you're, you know, and so it's a vulnerable, you know, for me, it's a highly vulnerable profession. And so, you know, you're not naked, but you feel it, you know.
The question is, what's the biggest mistake you made in the early days of NVIDIA, and what did you learn from it?
Let me give you an example of what somebody might say, and I will say, I'll say that that's not. And so anybody who knows our history would know that the first generation of our products, the architecture, the technology we used was completely wrong. It's not like a little bit wrong. It's like completely wrong. The fact that smart engineers and professionals, and we were actually funded, and we created this thing, and it's like, check it out. Doesn't work at all, you know? And so that using curved surfaces instead of triangles, no Z buffer instead of Z buffer, forward texture mapping instead of inverse texture mapping, we did everything wrong. No floating point inside. We did everything wrong. And so we made a lot of tremendously bad choices. I'll say that those are technical bad choices, but it led to strategic genius moves. How do you take a company that had that reputation and wasted a bunch of money and a bunch of time, 2.5 years, doing it the wrong way and surrounded by competition, and now here we are, the only one remain. Okay, and so that transformation taught me a lot about the importance of technology is important, but strategy is so important. And so how you see the world, how you approach competition, how do you approach the market, how do you conserve resources and apply resources, those decisions, I learned more in my early 30s through that deep failure and the company almost vaporizing. I learned so much about strategy and strategic thinking and maneuvering and things like that, and it's lasted a whole long time. The mistake that I made, that I would say was a genuinely straight up mistake, is when the PC or when mobile devices took off, we were approached by very important companies that are important in the mobile space to work on some mobile devices, and the choices that I made, I think the answer when they approached us, the answer should have been, nah, not interested. But we decided to shift a bunch of our resources to go build mobile devices, and I thought that we could add a lot of value, but it turned, I think if I would have thought through it a couple more clicks, the amount of value you can really deliver for the things that we know how to do and what we're good at is probably marginal at best. And so I shifted the company to go into mobile devices. It grew into $1 billion business, and that kind of positive reinforcement. And then shortly after, during the 3G to 4G transition, we were just 100% locked out. And Qualcomm was the leader in that 3G to 4G modem, and that's the most important part of the phone, not the SoC, not computer graphics, not even the application processor. The phone is obviously the most important part. And so during that transition, they were able to block us out. I could have probably called it, if that circumstance were to happen again, I would have said, yeah, it would be a really interesting opportunity for a couple of years, but we're going to get shut out after that. So what's the point? Why? Let's go conserve our resources somewhere else. But the recovery, so we got shut out. We built it up to about $1 billion and then went back to zero. But the recovery was I took all of that expertise, that extreme low power and energy efficiency expertise, and I shifted all to an application that didn't exist at the time called robotics. And so all of somebody mentioned Thor. Thor is the great grandson of the chip that we were using in mobile devices. And that entire genealogy and all the teams and all the expertise that we built up was really helpful to getting here. And so that's rationalization. Going into that market in the first place was a waste of time. And so that I think is a strategic mistake.
On strategy, is there, sometimes strategy is about forecasting sort of precisely enough. Is there, from a systems perspective, what do you think you've updated your priors on, or what is the forecasting mechanism you've developed to give yourself some confidence that like this fog of war here, don't quite know where things are going to go, but generally speaking, we're shooting in the right direction? Is there sort of a piece of system design advice you'd give folks on when the shape of the future is not entirely clear?
Yeah, and in fact, you used all the right words already. The first thing I do is what am I observing? What am I observing? And based on what I observe, let's reason about it back to first principles, break it all back down, and ask ourselves, so what's going to happen next? And first, so what? Is this a big deal? Hey, deep learning, computer vision, AlexNet, big deal. Is that a big deal or not a big deal? And so the big deal part of it is, my goodness, in just one, here's two engineers, right? Alex and Ilya and Hinton, of course, and they came up with a neural network model, and boom, it crushed the computer vision capabilities of all the computer scientists, decades before them in one shot. And so is that a big deal? Is that a big deal? the step up in quality and performance was a big deal. Now the next question is, so what's going to happen next? How far can you take it? And then if you could do it in this way, what else can you solve? And if this was able to solve some really amazing problems, what does that mean to computers and computing? And so you just keep asking yourself these questions, right? And so you're just iterating it like that all the way to first principles, and then from that you create a mental model about the future of computing. And where is it going to be? What can it do? For example, self-driving cars and robotics. How large would models become? And if so, what would computers look like? What would processing neural networks? How is that different than processing, floating point numbers and integers and first principle mathematics? We express everything in FP64, FP32, but obviously neural networks don't have to do that. And so you reason through it kind of like this. And then you build up a mental model of a future, of the future, and then where your company, where you are going to be within it, and then you just work backwards from there. And then now the question, of course, is you could be wrong. And oftentimes if you reason about things properly, you're not completely wrong, but you're not completely right. And so I tend to be very comfortable saying, okay, these are the things that will likely happen. And these are things that will absolutely happen. And these things may happen. And based on that, I think we ought to go in that general direction, and we'll feel our way through. And now the skill of building companies, then, of being successful along the way, is you're going into this direction, and it's going to take energy, it's going to take time, it's going to take money, and everything that time, energy, and money, that takes away from something else, right? So the cost, the opportunity cost of pursuing a strategy is the real cost. And so you just got to ask yourself, how can you be smart enough such that the opportunity cost is reduced and your optionality is increased? And so you're trying to think through all of that stuff all the time. It's no simple answer, but in a lot of ways, you're trying to get the journey to pay for itself.
Given everybody's going to mob you for more signatures,